Hello, welcome to today's video. My name is Prabjot Kaur, and what we are going to learn in today's video is the difference between linear regression and logistic regression. These two are basic machine learning algorithms, and it is very easy to confuse between the two, especially if you haven't used them in a while. So for some of you, this video may just be a refresher video. So let's get started. What we're going to cover in this video is, firstly, we're going to cover basics such as the difference between classification and regression. We're going to go over what is a supervised machine learning framework. Then we will dive deeper into linear regression and logistic regression. We'll have a lot of math, but I'm sure you will follow along. So let's go to the first discussion point, which is what is the difference between regression and classification? Broadly speaking, regression and classification are two types of machine learning problems. The difference here is that for regression, the target or the predicted outcome can be a continuous number. So meaning the predicted output can be any real number, such as, let's say you want to predict the house prices based on certain factors. Let's say you want to predict the stock price based on certain factors. These are examples of regression because your output can be any real number, theoretically speaking. Now, classification, here the target or the predicted outcome is discrete, meaning you can only have certain set of possible outcomes. So we can have either binary classification where the outcome can be only two possible classes, such as a positive class or a negative class, or you can have a multi-class classification problem where you can have more than two classes as an outcome. As an example, let's say you have an email and you want to classify whether the email is a spam or no spam. So that would be an example of a binary classification. So again, the difference is that for classification, the output is discrete, whereas for the regression, the output is any real number. So now we know that. Let's move on to the next slide, which is going to be about supervised machine learning. Now, there are several ways to train machine learning models. So one of the way is supervised learning. So in the supervised learning, the way we train a machine learning model is using labeled data. So what we're given is we're given a set of inputs. Those could be, let's say, images. And we have also the output associated with each image. So let's say my problem is that in the images, I want to identify which image contains a cat, which image contains a dog. So in that case, somebody has to label the images first. So then we have set of labels, set of input images, and that will be our labeled training data. The goal here is we want to find a function, or in other words, a model that associates this set of inputs, which is images in our case, to the correct outputs, which in our case is whether the image contains a cat or a dog. So the goal is we want to find the machine learning model that best fits the data. And this is called training a machine learning model. So if I have to show it in form of a mathematical formula, so y is the output and x is the input. These could be any kind of input like images or audio or text. And then we want to learn the association between this input and the output, and that association is done by this function f. We also call it a machine learning model. So we want to learn this function, and that's machine learning. And why do we want to do that? So the reason why we want to do this is that, let's say we have already learned the association between input and output. So now we have a model that has some knowledge. So we will take this trained machine learning model, and we can give it any new input that it has never seen before, and we expect it to predict the correct output. So that's the supervised machine learning paradigm. In today's video, we are going to talk about two types of machine learning models. So F could be anything, so any machine learning model. So today's focus is going to be linear regression and logistics regression. Okay, so far we know what is classification, what is regression, and we know what is supervised learning. Now we will get deeper into understanding what is linear regression and what is logistics regression. First, we will start with linear regression. Here, I want you to pay close attention to the slide. So pictorially, this is what linear regression and logistics regression looks like. So on the left, we have linear regression. So here, what you see is the x-axis goes from 0 to infinity, and y-axis also goes from 0 to infinity. And we have bunch of data. So these yellow dots are just data. So, and we know for a particular value of x, what is the value of y, as you can see here. So it's easy to tell from the graph. Our goal here is to fit a linear function, in this case a linear line, to the data. So that's why this is called linear regression. Again, why is it called regression? Because the output, which is y, can be any real number. So that's why it's called regression. And why is it called linear? Because we're trying to fit a linear model, in this case a linear line, to our data. So it's linear regression. Now let's look at the right. On the right is logistics regression. Here, I want you to pay close attention to the y-axis. So y-axis goes from 0 to 1, and x-axis goes from 0 to infinity. Here, we are trying to fit this S-shaped curve to the data. And this S-shaped curve is called a logistics function. And that's where the name logistics comes from. The reason why it's called regression is because the output, which is a y variable, although it is bound between 0 and 1, it can be any value between 0 and 1. So it's not discrete. That's where the word regression comes from. So the key difference is that here we're trying to fit a linear model. Here we're trying to fit this logistics function. Now, the other thing that you may notice is that I have this something called decision threshold. The reason is logistics regression by itself is a regression model. However, we have extended it to perform classification by defining this threshold. Usually, people pick this threshold as 0.5, and we say that if y is above 0.5, then that belongs to one class. If y is below 0.5, less than 0.5, then it belongs to the second class. So this logistics regression is actually used to solve classification problems. Whereas on the other hand, linear regression is used for solving regression problems. So fundamentally, this is what linear regression and logistics regression is. But we should try to investigate more and try to understand mathematically what is linear regression and logistics regression. So the next few slides, we will learn mathematically what is behind this line, what is behind this S-shaped curve. Okay, let's move on to the details. So as we saw in the previous slides, this is a linear regression plot. So let's start with the basic equation. You probably remember from your mathematics class that the equation of a line is y equals mx plus b, where m is the slope and b is the y-intercept. So that's the equation of the line. So what I've written here is nothing different. So we have intercept, which is w0, and we have slope, which is W1. So this is simply the equation of the line, and it is the equation of this line. However, in machine learning, you may have a more complicated problem than having just single independent variable that impacts the output. So let's take an example. Let's say you want to predict the price of houses. Now, we know that the price of a house depends on a lot of different factors. It depends upon the location, it depends upon the schools in that area, it depends upon the job types in that area. So there are several different factors that impact the price of a house in a particular location. So we want to take in all those factors. So in that case, the input is not going to be a single feature. We're going to have multiple features that impact the output. So we can generalize this equation to have more than one input. So here we have x1, x2, and x3. So these are different features. So in the case of the house price example, let's say your x1 can be the location, x2 can be the school types in that location, and x3 could be the job availability in that location. So these are different features that affect the outcome of a home price. However, all these features may impact the house in a different way. So this W1, W2, W3 is the weight. Like how much impact does the location have on the house price? How much impact does the school types have on the house price? How much impact does the job availability have in that? How much effect does the job availability have on the price for a particular location? So these are weights. So essentially, all these different features, when we combine them linearly, we get a linear model, and we call this linear regression. So essentially, the linear regression is simply the weighted sum, these are weights, of input features. So x1, x2, and x3 are input features. So just some linear combination of input features plus this extra term which we call bias. Now I can rewrite this equation in the matrix form. So basically I take all these weights W0, W1, W2 and put them into one matrix. And then I also take all of my input features x1, x2 and x3 and I put them into a different matrix. And I take the transpose of this matrix and multiply with the input features. Essentially, when I multiply this out, what I get is this equation up here, W0, W1 plus x1. You might notice that I have 1 here. And the reason is that because as you notice, W0 is not associated with any input feature. So when we try to multiply these two matrices, we need to make sure that there is a corresponding term that we multiply this with. So W0 times 1 is W0. Okay, so these two equations are exactly the same. It's just the matrix notation of this equation. We can make it even smaller. So briefly, we can take all of this matrix we can take this matrix of weights and give it a variable W. So this is just a matrix that contains all these weights. And similarly, we can put all these input features into one single variable, which we call x. So this x is nothing, but it contains all of the input features. So this is linear regression. In the machine learning terminology, what we call this y is the output, W0 is the bias, W1 is the weight, and x is a particular input feature. So if we want to generalize this, so again, y would be a vector of outputs, W is the weight matrix, and x is the feature vector, like number of features, input features. So before we move forward, just one thing I want to point out is that when we train a machine learning model, like first of all, why do we need to train a machine learning model? Because we actually don't know what this line looks like. So we don't know what is this W0 and what is this W1. And that's what we want to learn from the data. And that is called training a machine learning model. We are not going to cover in this lecture how we train the linear regression, but I want to point out that when we train a linear regression model, what we are trying to learn is this W0 and W1, or in other words, we want to learn this weight matrix. Okay, now let's move on to the logistics regression. Before we go into logistic regression, we have to understand what is a logistic function, because that's what is at the core of logistic regression. So logistic function is nothing but this function that you see here. It is equal to 1 over 1 plus e to the power negative t. And if we plot this function, it is basically this S-shaped curve that can take any input. So t can be any number. However, the output is bound between 0 and 1. So this is called sigmoid function or logistic function. And this is what we use in the logistic regression. So now we understand linear regression and we understand logistic function. Now we can put things together and build the logistic regression model. And we will do that in the next slide. Okay, so to start with the logistic regression, we will start with the same equation that we have for the linear regression, as you remember from the previous slides. So this is just the simple form of linear regression where you have just one input feature. Then if we apply logistic function to this output, to this y, like this, so we take this logistic function which we defined in the previous video, which is 1 over 1 plus e to the power negative t, so that S-shaped curve. If we apply that logistic function to the output from this linear regression, what we get is a new output. So as you know that y could be any real number for the linear regression, but when we apply the logistic function, this y bar, the new output, is going to be a number between 0 and 1. So we have transformed the linear regression into logistic regression by applying a logistic function. So essentially that's what logistic regression is. However, we are not done yet. So let's see what's next. So here I'm just taking this the value of y, which is w0 plus w1x, and then plugging it in here, taking a sigmoid of that. So nothing fancy. I'm just plugging in the this variable now, w0 plus w1x, into the logistic function for this t. So that's all I did. So this will give us a number between 0 and 1. So as you know, logistic regression is used for classification problems. So how do we take this number between 0 and 1 and turn that into a classification result? The way we do that is by defining a decision threshold. So we define a decision boundary and we say that if this y bar is less than that threshold, then we want to classify that as some class 0. If that y bar is greater than 0.5 or equal to 0.5, then we want to classify the result as belonging to the positive class. So that's what logistic regression is. So essentially, the output is the logistic, this y, of the weighted sum of the input. So we still have the weighted sum of the inputs, but we have applied the logistic function to that to get this y bar, and then we apply a threshold on top of it, and we get a result for the classification problem. So now you know what is linear regression and logistic regression. So to conclude, what we learned in this video is the difference between linear regression and logistic regression. We learned about the logistic function, which is at the core of the logistic regression. So to sum it up, the linear regression is the linear combination, weighted combination of the input features, whereas the logistic regression, here you also have the sum weighted linear combination of the inputs, but we apply the logistic function to that, and then we define a threshold and we get our logistic regression. So linear regression is used for classification problems, and logistic regression is used for linear regression is used for regression problems, and logistic regression is used for solving classification problem. So that's really what we wanted to learn in this video. So what's next? So the important thing is we actually don't know what is this W0 and what is this W1 for machine learning tasks. And that's what we want to learn from the data, from the labeled data. So essentially, what we need to know next is how to train this linear regression model or logistic regression model. And that's what we have not covered in this video. And I encourage you to spend some time to learn how to train the linear regression and the logistic regression model to complete the full picture. And I may have a video in the future to cover this concept as well. For now, that's all for this video. I hope this was helpful to you, and if you like the content, please subscribe to my channel, and that really helps me a lot, and it gives me a lot more encouragement to make these type of videos to keep everybody learn from these, and I learn too. And when I make videos, I learn new stuff, and I like to teach. So I would love to have you as part of my channel. Thank you for now. I'll see you in the next video. Bye.